In this video, we're going to talk about inverse functions. So first, let's define an inverse function. F and G are said to be inverses of one another if and only if the fog of x equals the gof of x, which equals x. It's not so much that this equals this, but rather that both the fog function and the gof function give you back x. Now, by definition, this means f evaluated at g of x, and this, by definition, of course, means g evaluated at f of x. So, how about we look at some problems where we try to calculate the inverse, or we verify that two functions are inverses. So you have f of x equals x cubed, and g of x is equal to the cube root of x. Are they inverses? Now, inverses, sometimes you can just say yes, or of course these functions are inverses. Notice that gof of x undoes whatever f of x did. That is, you do f of x to something, and then if you do g, it undoes it. That is, you get back what you start with. For example, if you have a number in your calculator, 7, and you cubed it, and you get back, your calculator now says 343. But, like me, you have a short memory, and you forget that you had 7. You forgot that you just cubed 7. And you're like, oh my, I didn't mean to cube 7. I meant to add, I didn't mean to cube. If you knew it was 7, you'd be okay. You didn't mean to cube it. Maybe you meant to add 3. Maybe you meant to multiply by 3. Well, how would you get back the 7, or whatever that number is? Well, to undo what you just did, namely the undo cubing, you take the cube root. See, yes, these two functions, f and g, are inverses of one another. F does something to x, maybe it cubes it, and then g takes the cubing and it computes the cube root of it, which gives you back what you started with. So yes, these two functions, f and g, are inverses, but we want to prove this. Prove that these two functions are inverses. So you need to verify two things. You need to verify that this equals x and that this equals x. Once you do that, you're okay. Well, this means f of g of x. Oh, the g of x is the cube root of x. And what's the job that f does to whatever you put in there? You cube it. They put that in there. I couldn't care less what it is. I'm going to cube it. Well, that gives us back x. We're halfway done. Gof of x means g evaluated at f of x. But f of x is x cubed. Well, what does g do? It takes whatever inside the brackets, and it takes the cube root of it. Okay, I couldn't care less what's in between the brackets For right now, I'm just going to denote that I'm taking the cube root of it. And yeah, the cube root of x cubed is x. So I satisfy both conditions. This had to equal x, and the graph of x had to equal x. So f and g are inverse functions. One undoes the other. That's what inverse functions do. They just undo what the other function did. Okay. Suppose that you were given a function and you're asked to find the inverse. Now, sometimes it's just a matter of thinking about it. If you're given that f of x is equal to 5x plus 1, and you're told to find the inverse of x, well, let's see what was done to x. Like, for example, if I were to tell you x is 7, wouldn't you first multiply 5 times 7 and then add the 1? You would do that first, and then adding second. First, and then the second. Well, how do you undo it? Well, you take your answer, which is x, and, well, you take away the 1. I mean, after all, if I take away 1, I'll have 5x, and then you divide by 5. That's the inverse. Just undo what you did. Again, you have some number in your calculator, you forgot what it is, and then you multiplied it by 5 and added 1. What do you do to this result? Let's call it a triangle. What do you do to the triangle to get, so this is known. That's what's in your calculator. All you remembered was you had this number, you sure wish you knew what it was. But you multiplied it by 5 and you added 1. Well, if you take away 1, then you'll have 5 times the number. Divide by 5, it'll give you the number. But generally, we'll call that number x. And that's exactly what I got. Another way to do it is as follows. Let's start with x and let's see what f does. What does f do? Well, first, it multiplies by 5. So now we have 5x. And then it adds 1. So you have 5x plus 1. Call that the new x. Now you need to undo what you did. To undo adding 1 to this value, take away 1. And now this is what you have. Oops. Now, to undo multiplying by 5, we are going to divide by 5. And that's going to give you x minus 1 over 5. So, let me do it with the same notation that I did before. So, to undo adding the 1, we take away 1. So now you have x minus 1. And to undo multiplying by 5, you divide by 5. What you get here, that's f inverse of x. Okay. A more formal way, this generally works all the time. You have that f of x is 5x plus 1. Call that y. Y equals 5x plus 1. You could interchange, you should interchange x and y and solve for y. That is, take away 1 from both sides Now you have 5y is x minus 1. Divide by 5. Now you have the y is equal to x minus 1 over 5. And now change the name to y inverse. Because if you interchange x and y becomes x, but x becomes y inverse. I mean, we could have done that right here, right there. When I interchange x and y becomes x becomes y inverse. And there is your answer. Just interchange x and y. That is one way to find the inverse. Now, let's talk about how functions will look if they're inverses of one another. Suppose f of x is 2x. Well, I hope it's clear that to retrieve x, you should use the function that divides by 2. Just divide by 2. And again, if you don't believe that, you can say y is equal to 2x, interchange x and y, but instead of y, write y inverse, then divide both sides by 2, and x over 2 is y inverse, like I said. Now, if you were to graph these two functions, well, y equals 2x is just a straight line, and it's easy to get points on it. Pick an x and double it and call it y. Well, I'll pick 0, I'll double it, I get 0. I'll pick 1 and I'll double it, I'll get y. And maybe I'll pick 2 and I double it and I get 4. Well, that was pretty easy. It gave me 3 points. 0, 1, 2, 1, 2, 3, and 4. So when x is 0, y is 0. When x is 1, I go up to 2. And the reason we pick a third point is 2 points, say the 2 points I plotted, guarantee me a straight line. But now, if you plot the third point, I'm going to plot it incorrectly. If you plot the third point and it's up there, I hope it's clear that these 3 points do not lie on a straight line. So you go back and you find your error. Probably a better error would have been the following. Suppose the second point you got wrong. Now, if you didn't know the second point wasn't over here, you would draw this line. You would draw that line and you'd be wrong. But if you draw a third point, you would have seen, hey, those 3 points don't lie on a line. Oh, I plotted that point wrong. It should have been here. So now you have this line. Okay. And this is y, or f of x, equals to 2x. Now, let me just draw this a little bit lower as well. Now, let us plot the other point, the other graph. Y is equal to x over 2. So if you divide x by 2, you get y. So you know, I'm going to be smart about it. I'm going to pick x values that I know how to divide by 2. When I divide 0 by 2, I get 0. When I divide 2 by 2, I get 1. And when I divide 4 by 2, I get 2. So those are 4 quick points. Sorry, 3. 3 and 4. And I also have 0, 0. I have x is 2 and y is 1. And I have x is 4 and y is 2. I have this line. Now, if you consider the line y equals x, if you consider this line, y equal x, the green and blue and the pink lines are mirror images across that blue line. Y is equal to x. Y over here is x over 2. They're mirror image. In other words, if I go to the blue line at a right angle, whatever that distance is, and please don't give me a hard time if my graph doesn't look like this, but that distance is going to be the same. Whatever distance this is, have to go with a right angle, this distance is going to be the same length. If I go over here that amount, and over here that amount, I'll hit both graphs. They're equidistant. They're always in other words, if you were to put green paint along here, if you were to put green paint along here, say on your paper, and then you folded your paper along the line y equal x, you folded it along this line, what you're gonna have is green paint right there. Their mirror inverses are mirror images across their line y equal x. In fact, whenever you have like y equals 2x, it contained a point on the line y equal x. Clearly, y and x are equal. It happened to be right there at the origin. Well, it's going to be true that that point, that graph, y equal x over 2, is going to have that same point. Why? Because both of these, the original green graph, y equal x over 2, is 0 units away from the blue line. So the pink line must also be 0 units away from the line of symmetry, the line y equal x. They're both 0 units away from the origin, which happen to be where the two lines met the line y equal x. If one line crosses y equal x, the other line will also cross y equal x. One reason is because if you switch x and y, which inverse will do, that 0 originally was x equals 0. So now I make it y equals 0. This 0 was y equals 0. Now x is 0. Oh, yeah, I have that point 0, 0. And you know what? X is 1 here, y is 2 there. Here it's reversed. Now x is the 2 and y is the 1. 2, 4. Here I'm going to have 4, 2. X and y got switched. X and y got switched. So here's a good exercise to show that. Suppose you come to know that f of x contains the points, say, 0, 2, negative 3, 1, and 1, 3. If f of x contains those 3 points, and please, if you're going to plot them, here's 0, 2, here is negative 3, 1, and here is 1, 3. Do not draw a curve. Do not draw a straight line. because you have no idea if f of x contains that point or that point or that point. I mean, it could have gone like this. It could have gone like that. Or f of x could only contain those 3 points. Okay, so if f of x contains those points, then f inverse of x must contain what? And the answer is switch x and y. It must contain 2, 0. It must contain 1, negative 3. It must contain 3, 1. Because the only difference between this function and this function is we switched x and y. Okay, so x got switched and y got switched. X used to be 0, now y is 0. Y used to be 2, now x is 2. Why? Because the points on the bottom are the inverse of the points on the top. So now, how about this? Suppose I tell you that, so I'm just going to draw this line first, y equal x. Suppose you come to know that f of x looks, well, let's draw it so it's a function. Suppose you come to know that f of x looks like that. That's f of x. Y equals f of x. So the question is, how would you draw the inverse? Now, if you didn't have the pink line, my advice would be the first thing you should do is draw that pink line, y equal x. Let's even label it. Y is equal x. Wow, just draw the mirror image. Looks to me like it would be something like that. And that is y equals f inverse of x. Inverse means x and y were switched. And this looks pretty good because this distance seems to be the same as that distance. This distance seems to be the same as that one. And if you want to say, no, it isn't, fine. I'm not going to argue with you. Draw it better. Draw it better than I did. This distance is the same as this distance. Now, this point on the green line is right on the pink line. So, the blue line, the blue curve, must also be right there on the pink line. They're both 0 inches, 0 units away from the line y equal x. Same thing up here. And the same thing here. If f of x crosses the line y equal x, then f inverse of x will also cross that same line. So given a function like the green function, y equal f of x, you're able to draw the inverse function if it has an inverse. If it has an inverse. Some functions do not have an inverse. Let's do one more problem, and then we will talk about functions not having an inverse. Okay, suppose that f of x is x over 2, and g of x is x plus 1. Well, those are not inverses. But the instructions is to find f inverse circle G of 7. Oh my goodness, what is this? Well, they're asked, so, you calm down, you ask yourself, what are they asking you to find? They want you to find this. Well, we know, just because we have strange names for these functions, f inverse, g inverse, it doesn't matter. It means this. Okay, so I know one thing. Before I can find f of this, I need to know what that is. Well, I have g of x. Well, this here is an x value. G inverse of 7 is equal to x. Okay? Now, if I interchange those two, because that's the y value, if I interchange those two, then I have to drop the inverse. I get that g of x is equal to 7. But I know that g of x is x plus 1. That equals 7. Ooh, 6 plus 1 is 7, so x is 6. Remember, this equals x, which is 6. So it's f inverse of 6. Now, what on earth is f inverse of 6? Well, again, usually f for something is a y value. So am I going to say this is a y value? No, because this is f inverse and x and y were switched. This is an x value. Now, if I interchange those, I get x here and 6 here. But then I have to get rid of the inverse. F of x is 6. Well, I know that f of x is x over 2 on one hand, and on the other hand, they're telling me it's 6. Well, 2 times 6 must equal x. X must be 12. That is, f inverse of 6 must be 12. And that's how you would do that problem. You have to think. Okay, there's no formulas all the time in math. You have to think. Okay, now, suppose you have the following. F of x is x squared, and g of x is the square root of x. And the question is, are f and g inverses? Are they inverses? Well, the very first thing I wrote was the definition of inverses. We need to verify that the fog of x is equal to x, and that the gof of x also equals x. Okay, well, this is f, by definition, this is f of g of x, and g of x is the square root of x, and if you square the square root of x, because that's what f does, whatever you put in the brackets, it squares it. So if you plug this in, you're going to get the square root of x, quantity squared, which does equal x. Okay. So that's good. It's looking promising. This is equal to g of f of x. And before I can do g of that, I need to know what that is, and that's x squared. And whatever this is, what does g do to what's in the brackets? It takes the square root of it. Okay, well, this is in the brackets, and I take the square root of it. And you know what? I don't get back x. I do not get back x. So we conclude f and g are not inverses. Now, of course, some of you are saying, of course, the square root of x squared is x. That's nonsense. Suppose that x is -7. The square root of -7 squared. Well, before I can take the square root of something, I have to know what the something is. And the something is whatever -7 squared is. But that's 49. And I know what the square root of 49 is. It's 7. Look, I didn't get back x. I plugged in -7 for x, but I didn't get back -7. If I plug in -5, this gives me the square root of 25, which is 5. I didn't get back what I plugged in. But what if I plug in 4? 4 squared is 16, and the square root of 16 is 4. Ooh, this time I got back what I plugged in. Let's do one more. If I plug in 9 and I square it, that's 81. Ooh, the square root of 81 is 9. Oh, I got back what I plugged in. Well, let's think about something. What type of function, when you plug in 7, gives you back, when you plug in -7, gives you back 7. When you plug in -5, it gives you back 5. When you plug in 4, it gives you back 4. When you plug in 9, it gives you back 9. That is, what function behaves like that? And the answer is the absolute value. The absolute value of -5 is 5. The absolute value of -7 is 7. The absolute value of 4 is 4. The absolute value of 9 is 9. That is. A more complete answer here would have been that the square root of x squared is equal to the absolute value of x, which is not x. Okay, so then we conclude that f and g really are not inverses. In other words, if you have -7 in your calculator, and by accident you square it, so now your calculator says 49. And you're like, darn, I didn't mean to square it. It took me 3 hours to get, I have this really, really long calculation to do. And so far I've been working for 3 hours. And I had this number. I just squared it and I got 49. And I'm like, I didn't mean to square it. I meant to do something else. Maybe I meant to divide by 2. I meant to add 29. People make mistakes. So you may say, well, you know what? To undo squaring, which was my error, I didn't mean to square, I'm going to take my answer and I'm going to take the square root of it, because that's going to give me back my answer. No, it doesn't. Squaring is not invertible. You can't invert squaring. Okay? Because if you square, plus or minus 7, you get back 49. But when you take the square root of 49, you only get back 7. And even if you did get back plus or minus 7, even if you did, was it the 7 squared they gave you back? Or, did it give you back -7, and maybe the -7 gave you back +7? That is, maybe you input -7 and it gave you back +7. But it doesn't matter, because you don't get back plus or minus 7. Okay, so some functions are not invertible. And these functions are ones that fail the vertical line test. Okay, sorry, the horizontal line test. And let's look at x squared, the one that just failed. Well, if you square a number, and this time you get back, I don't know, 64. The problem is, I can't tell you what number you squared. I can tell you, so it's a game. I squared a number and I got 64. What's the number did I square? Well, I don't know. It's either plus or minus 8, you know. And you say, all right, I'll try to make it easier. I squared a number and I got 16. What number did I square? I don't know. Either you squared this number, which of course is 4, or you square that number, which is negative 4. I apologize that my scale is so off, but you see the point. This horizontal line at 16 crossed the graph 2 different places. This horizontal line at 64, it crossed the pink graph, y equal x squared. It crossed it twice, here, here, and here. That's what gave us negative 8 and positive 8. So I can't undo the squaring. But if we had x cubed, that's a whole nother story. X cubed goes this way. And it never fails the horizontal line test. No matter which horizontal line I draw, it only crosses the graph in one place. No matter which horizontal line I draw, it only crosses the graph in one place. So, if I tell you that this height is 8, well then, it's 2 that I cubed. Just for the record, negative 2 cubed will be negative 8. If this height is negative 8, well then, there's only one answer, negative 2. If this height here is 27, then x is 3, because 3 cubed is 27. This horizontal line does not cross the curve, which is in pink, in but one place. This horizontal line only crosses the graph in one place. Now, just for the record, if the graph stopped right there, well then this horizontal line crossed the graph in no place. That's okay. And maybe the graph, I don't know, well, okay, maybe the graph ended up there. So this horizontal line crossed the graph in no place. That's okay. You just can't have a horizontal line that crosses the graph in 2 places. That's what you can have. For example, is this function invertible? That means, does it have an inverse? Now, the function only has an inverse if and only if it passes the horizontal line test. So, suppose you have this graph. And this graph has an open circle here, and it has a point up here. You know, let me draw a more familiar graph so we could talk better about some points. What I have on the board right now is x cubed. But I'm going to remove one point. I'm going to remove that point right there. Okay? and I'm going to put it up here. So, and let's say that's 2. So f of x is a piecewise function. It equals to x cubed if x is not 2. And it equals to 10. It equals to 10. You know what? Let's make it 16. It equals 16 if x is 2. Ooh, if x is not 2. Now, whether I define the function below or not, that is, if you just were given this graph is not one-to-one. It fails the horizontal line test. Not because of that line, because it only crossed in one place. Not because of this line, it only crossed in one place. Not because of this line, it only crossed in one place. Not because of that line, it crossed in one place. Certainly not because of this line, because that line crossed the graph nowhere. But you know, and not because of this line, it only crossed the graph in one place. But you know what? This line crossed the graph here and there. It crossed it in 2 places. Now, I want to just move that point a little bit more to the right so it's more believable to be when x is 2. Now, if this height was 16, okay, that means f of 2 is 16, and you know what? It's not going to matter, but I'm sorry about keep changing things. Let's call it 27. F of 2 is 27, and f of 3 is 27. So make believe that height right there is 27. Well, again, f of 2 is 27, and f of 3 is 27. So if I tell you that f of x is 27, you can't give me back one x value. You're going to say x is 2 or 3. Well, that's not a function. So, you know, this would be the inverse. It's not a function. You can't plug in. So in other words, f inverse of 27 will equal to 2 and 3. But that's not a function. I don't care if we call it inverse or not. If f of 27, or sorry, f inverse of 27 gives me back 2 answers, it's not a function. Just like if I have, this graph, it's not a function, because when x is that number right there, it fails the vertical line test. It crosses the curve here and here. That's not a function. Okay? I can take, you know, make believe this is 2. I take f for 2 and I get, I don't know, call it a and b, whatever those numbers are, but they're not the same numbers. I get back a and b. F is not a function. I take f inverse of a number. I get back 2 values. F inverse isn't a function. Okay? The inverse function must be a function. So basically, so let's just look at this from another viewpoint. This here is a function because it passes the horizontal line test. Okay? It's a function. And, you know, maybe this was the axis. Okay? So it's a function because it passes the horizontal line test. But now, if we interchange x and y, which inverses do, now remember, well, let me just put it back to the typical x and y for a moment. So, for any given x, you should only have one y. So, for example, for this x, did I do that backwards? What is wrong with me? Scratch that, I apologize. This is a function because it passes the vertical line test. This is a function because it passes the vertical line test. That is, for any given x value. For this x value, you go down and up, it only crossed one place. For a given x value, it's only supposed to cross one place. Given this x value, go up and down. Oh, it only crosses one place. It can cross no places, all right? Imagine the graph ended here. So then, for this x value, I go up and I go down and it doesn't hit the graph. It's still a function. Now, if you interchange x and y, well, initially the lines I drew were parallel to the y-axis. Well, now the y-axis is horizontal. So I draw my lines horizontally. Ooh, that too is a function. Okay, just because f of x is a function doesn't mean that f inverse is also a function. Just want to really stress that. This here is a function. Y equal x squared, or whatever this graph is. This is a function. Why? Because it passes the vertical line test. No matter which vertical line I draw, it doesn't cross the graph in more than one place. Okay, so f of x is a function. Also, if f is a function, so is f inverse. Nonsense. This fails the vertical line test. This vertical line crossed in two places. For the record, this vertical line crossed in one place only. This crossed nowhere. But I can find at least one line. Doesn't have to be more than one, but I found one line or more that crossed the graph twice. So f inverse of x is not a function. Now, before you can talk about the inverse of a function existing or not, before you can talk about the inverse of a function, like the inverse of the function f of x, it's implicitly understood that f of x must be a function. Okay, we're not ever going to talk about the inverse of that function. Why? Because that's not a function. It's a relation. I mean, it could have been a circle. That's a nice relation, but it's not a function. Why is it not a function? Well, first of all, I like to get rid of this piece here. Let me draw that a little bit better. You may say, oh, yeah, the inverse exists. The inverse exists. You know why? I hope you all see why. One might say that the inverse of this green thing is a function. And the reason would be, look at this, look at this. It never crosses No horizontal, it passed the horizontal line test. Any horizontal line I drew, it never crossed in more than one place. It never crossed in more than one place, so the green curve has an inverse. No, it doesn't. Why? Because the green curve is not a function. You can't talk about the inverse of a function if you don't have a function. It's like having a lengthy conversation about what you're going to do with your $1 million when you don't have $1 million. What are you talking about? Or, I'm not going to talk to you about your $1 million. You don't have it. We're not going to talk about the inverse of a function if you don't have a function. Over here, we don't have a function, but over here, we do. Y equals x squared, y equals x to the 4th, things like that. Okay, now we're going to talk about, and this is calculus after all, how can we use calculus to determine if a function has an inverse, it's invertible? Well, if the first derivative is always positive for all x, so, for this x is positive, for that x is positive, the derivative. It's getting less positive, but is positive. Positive, less positive, more positive, even more positive, a little less positive, positive, positive slope, more positive. This curve must be 1-to-1. It's always increasing. To fail the horizontal line test, you have to be increasing and then decrease. Then you fail the horizontal line test. But if you're only going up, even if you're going up like that, if you're always going up, you're always increasing, you'll never fail the horizontal line test. Likewise, if the derivative is always decreasing, or f prime of x is always negative for all x, it's always negative. So, negative slopes. So you have a very negative slope, less negative, more negative, less negative, the same negative, less negative, more negative, the same more negative, less negative, same negative, more negative, less negative. Well, this function is always going down. Again, the only way you're going to fail the horizontal line test is if you're going down and then you go up. That's when you fail. Okay, we're not going to prove this, but I just argued it, I hope, so you believe it. So, if f prime of x is greater than 0 for all x, or f prime of x is negative for all x, then not the derivative, but f of x is invertible. Now, I want to just show one more thing. Maybe I didn't do it so well. So, you have a positive slope, a positive slope, a positive slope, a positive slope, a positive slope. But then you have a negative slope. Then you have a negative slope. Well, the graph had to be going down. And that's where you fail the vertical line test. You can't, that's why it has to be for all x. The slopes have to either all be positive or all be negative. So, this is a test to see if our function is invertible. So, I guess a good function to test this on would be f of x is equal to x squared. Well, f prime of x is 2x, and f prime of x is greater than 0 if x is greater than 0. And actually, sometimes it can equal 0. If x is greater than or equal to 0, and f prime of x is less than 0 if x is, I don't want to say equal for both of them. That is, sometimes the derivative is positive, sometimes the derivative is negative. That is, it's not positive for all x. It's not negative for all x. Sometimes it's positive, sometimes it's negative, and it's allowed to be 0 sometimes. Okay, in other words, if it's positive, positive, less positive, 0, and then positive, and more positive, and less positive, and more positive, and then maybe 0 again, and then positive, this curve right here is invertible. Even though right here and right here, these two places, the tangent line is 0. Okay, so we conclude that f of x equal x squared has no inverse. Let's try one more like this. Without graphing, how would you show that f of x equals x squared minus x, well, has an inverse or doesn't have an inverse? Has no inverse. Well, you take the derivative. F prime of x is, now let's make it x cubed. So it's 3x squared, so even make that plus 1. Well, I like to think that there's 3 types of numbers. There's negative numbers, there's positive numbers, and there's the number 0. If you square a negative number, you get a positive. If you square a positive, you get a positive. If you square 0, you get 0. If you triple those numbers, if you triple a positive, it stays positive, just like over here. And if you triple 0, it stays 0. Well, if you add 1, this will stay positive. That would become 1, which is positive. And that's positive. So this is greater than 0 for all x. That implies f of x equals x cubed plus x has an inverse. The derivative is always positive. How can you quickly, based on this problem in front of us, how can you quickly come up with an equation that is for an f of x that's the derivative is always negative? Well, negate this. Say negative x cubed plus x. Remember, the derivative, it just keeps that negative in front, or negative 1 in front, and multiplies by the derivative of that. It's the constant multiple rule. keep the constant and take the derivative of the function. Well, we know that this is always positive. We just did it. You multiply something that's always positive by -1. It's always negative for all x. So, I just want to do one thing. Let us change the name. So, g of x, not g prime. G of x has an inverse. F of x has an inverse. Going to do one more problem. It's going to have a restricted domain. Suppose that f of x is equal to x minus 4 squared, but x is never less than 4. Well, this is just an x squared where the vertex is at 4. Forget this for a moment. It's this graph right here. And as we know, that graph fails the horizontal line test because that horizontal line, for example, crossed here and here. But we're not supposed to allow x to be less than 4. So all of this gets erased. All of that gets erased. And then the horizontal, let me just do that. So let's be clear that only this is the graph, and it passes the horizontal line test. No matter which horizontal line I draw, even down here, it never crosses the graph in more than one place. Here, those places it cross 4. I mean, one place each. Down here, it never crossed. Here, it doesn't cross. Here, it doesn't cross. But that's okay. It just can't cross more than once. So, it turns out that this graph does have an inverse. Now, how can we prove that using calculus? Well, f prime of x, you have a function to a power. Keep the function the same, bring down the power, make the new power 1 less, take the derivative of what's in there. So f prime of x is 2 times x minus 4 to the first. You don't have to put first, nor do you have to denote that you're multiplying by 1. Now, remember, the x has to be at least 4. Well, 2 is always positive, and if you have at least 4, if x is at least 4, if you have at least $4 or more in the bank, and somehow, so you go to the bank and you take out 4, you won't be negative. Either you'll have 0 or more. But that's all you need. The derivative has to be either 0 or all positive, or 0 or negative, not both positive and negative. Okay, f prime of x is greater than or equal to 0 for all x greater than 4. This implies f of x has an inverse. Okay, because the derivative is never both positive and negative. Now, I do want to just say one thing. What if you have a function like this? It's increasing here, and it's decreasing here. This function, so maybe it ends here and it ends here, and maybe they go up to the right and to the left forever. The thing is now, no matter which horizontal line you draw, it never crosses the graph in more than one place. For example, this line here crossed in no place. This line here crossed in no place. The other lines I drew, they all crossed in one place. So this does have an inverse. So I guess what I should have said, and I didn't, so let's go back and fix that. Okay, so it should be coming up about here. Does anyone know what I need to say to make this work? Okay. It should be, suppose F and G, sorry, just F. Suppose F is a continuous function, is a continuous function on its domain. Now, what on earth does that last part mean, on its domain? Well, on the domain, x is greater than or equal to 4, this function is continuous. I can draw it without lifting my pen. Can draw it without lifting my pen. It is continuous. And it has an inverse because the derivative is always positive. So you can have functions that just have this green part here, and maybe it goes up forever, and this green part down here, maybe it stops right there. Maybe the function is just in between those two dots, between here and here, and it looks like this. This function has an inverse, and you could draw the inverse. Goes like this, and it goes like that. All you need to do is consider the line y equal x and draw the mirror image. I would think that one goes like that, and it could be the same thing. It could be, depending upon how I drew it, it could actually be the same piece. Okay, so you have this green piece and this green piece, that's f of x, and the inverse is this piece and coincidentally that piece. Now, to make it real clear that two functions can be their own inverse is, suppose you have this function, so you have y equal x, and maybe you have this line which is perpendicular to it. you have that line which is perpendicular to it. This would be x plus y, say, equals 4. That is, y is equal to 4 minus x. If I interchange x and y, and for y I put y inverse, well, I get x plus, well, let me solve for y inverse. Oops. So I'm going to interchange x and y inverse in this last line. I'm going to interchange those, and I get y inverse is equal to 4 minus x. So y was 4 minus x, and so was y inverse. Again, if I put blue paint, heavy blue paint here, and then I folded the paper against the, I folded the paper along the line y equal x. Don't ask me how the paint is going to become a different color, but I'd get paint right there. I would get the blue paint right there. That is, it is its own inverse. And of course, the inverse of y equal x would be y equal x. Okay. This completes the section on inverse functions.